In this final video, I'll go through more of a qualitative discussion on soil shear analysis for downhill sliding failure, along with a series of design rules for mitigating downhill sliding. This is because when the anchor is above the foundation, we do not want to build a downward sloping ramp. Similar to how we use the bottom slope effects, which are in a different lecture for abutment sliding, to increase our sliding factor of safety, this configuration will result in a component of the abutment weight that is pulling the entire abutment downhill. And I've drawn out here along the shear failure length what our soil area will be, as well as just a quick graphic showing the weight of the ramp and how, if we have a downward sloping ramp, there will be a downhill force component that is acting against our resistance to sliding and contributing to our overall horizontal forces on the abutment. So here we have two options. Option one, if the anchor is slightly above the foundation but does not exceed the top of the foundation, like I've drawn here. In this situation, we will always draw a horizontal line from the anchor bottom to the foundation, or wherever it hits on the foundation, whether that be the top, which I've kind of shown here, or in the middle of the foundation, and we'll build our ramp wall horizontal. In option two, our anchor is significantly above our foundation, greater than the foundation depth, so we'll need to use steps. You can imagine this as the difference between, say, sitting on stairs versus sitting on a slide. Sitting on the stairs, you're going to feel more secure, whereas sitting on a slide, you're always going to want to be sliding downhill. And here are some steps I've drawn out for you. In both options, the soil shear failure plane is sloping downhill toward the river. In the event of failure at this plane, we would need to analyze the forces on a soil component. As you can see, at this angle, a portion of the entire abutment weight will contribute to the shear stresses on the soil wedge, just like it will contribute to that downhill sliding, which is causing the friction that's causing shear at the soil interface. This is demonstrated by the red equation on the right as the F sub V cos psi component, where I've defined psi as the angle of the soil shear failure plane off of horizontal. This component will almost always result in theoretical shear failure, unless we can do a more advanced analysis beyond our current scope, so that we start to look at more circle, we start to look at different failure planes, we start to look at different soil properties, right? But instead of doing this, we've consulted with geotechnical engineers to devise a series of design rules. Rule 1 is to maintain a 3-to-1 run-to-rise ratio for steps in the ramp wall or for the distance from the anchor to foundation if you are just drawing a horizontal line. In addition to maintaining that 3-to-1 run-to-rise ratio, we'll have 1-to-1 drops. As I've kind of called out here in the steps downward, we want these 1-to-1 drops to avoid shear concentration. And this is explained a bit further in the abutment sliding lecture. Rule number 2 is if the ratio is less than 2-to-1 run-to-rise of the soil steps, the design is not feasible. But if it's somewhere between 3-to-1 or 2-to-1, we want to check the design with the method I've shown above, and likely in the event that we're seeing a theoretical failure here, it may be necessary to check with the geotechnical specialist or work with your design engineer in charge further on the issue.